Hello and welcome to my second series of videos where today we will be working with non-ideal gases. And more specifically in this one video we will be working with a schematic PV diagram, and we will use this to demonstrate how the critical temperature is how the critical point is used to determine the A and B parameters in the van der Waals equation of state. And we will be deriving these expression of parameters and the critical compressibility. And yeah, let's get into it. Let's get started. So here we have a typical schematic PV diagram where the pressure is on the y-axis and the volume is on the x-axis, right? As we can see, the specific molecule or specific compound is changing and fluxing from the solid phase to the liquid phase to the gas phase and so on, back and forth between the three phases, right? And as we can see here, the big solid line of the schematic PV diagram of the molecule. Under we have these dashed lines where this is just a weird phase where it doesn't really happen necessarily, but we're kind of disregarding where it's half liquid and a half vapor while it's transferring into vapor. And this is like such a small change in pressure that it's not even seen as a change in pressure. It's only seen as a change in vapor or in volume. So as we can see up here, we have a point C, which is our critical point. And at this critical point, we have a specific isotherm, which is for the specific temperature, which goes with a specific pressure and volume, which we have here, right? And we also have three other isotherms, one for when the temperature is greater than the critical point temperature, and two for when it's lower, right? And if we zoom in here, kind of looking at the critical point, we see that it's an inflection point, right? We see that it is a point where the concavity changes. It is a point where from the left it goes from concave down to concave up, right? It changes concavity, so it is an inflection point. And if you remember from calculus, we know that inflection point causes it to have a derivative and a second derivative which is equal to 0, right? Because it is a flat point and it is an inflection point, we know that it is equal to 0. So we are able to use those two equations in order to solve for the A and B parameters of the van der Waals equation, right? So here I have already put in van der Waals equation of state, and as we know, it is equal to, or it is the pressure which is equal to the constant R times the temperature all over volume minus B, which is also a constant. This is subtracted from, or this is minus A, which is also constant, divided by the volume squared, right? So as we said from before, looking at this PV diagram and looking at the critical point, we know that the second derivative and first derivative is equal to 0. So let's put that into here so that we can start solving for some equations, right? So the derivative of the pressure with respect to the volume, right? And this is all when the temperature and the volume is the specific temperature and volume for the critical point, right? It's the critical temperature and critical volume, right? So T is equal to TC and B is equal to BC. We know that this is equal to 0. Right? We can also kind of find the derivative. Like we know the variables that are needed, and we can find the derivative, right? So we know that 0 is simply equal to negative of constant R times the specific temperature at the critical point. And this is all over the specific volume at the critical point minus B all squared, right? Because we're getting the derivative. Now, derivative of negative A minus B plus, or B squared, sorry. The negative now turns into a positive, right? Because we're multiplying by negative negative 2, and this becomes a positive 2a, right? And this is simply all over v cubed, right? And so we have our first derivative. As we said before, we also know that the second derivative with respect to v is also 0, right? Second derivative. And this is, again, when the temperature and volume is the specific temperature and volume needed for it to be at the critical point. Right? Just going to put this in. Right? As we said before, we know that it is equal to 0. Right? And again, we can solve for the second derivative from the first derivative we got, right? So this negative now becomes a positive 2. Right? So we have positive 2 times r times the specific temperature at the critical point. Right? And this is all over the denominator, but to the power of 3 now, right? So we have specific volume at the critical point minus the constant b, but now cubed instead of being squared, right? Now this plus 2a turns into a negative, right? Because we're multiplying times negative 3. So it becomes a negative 6a, right? Minus 6a all over v to the 4th, right? And now we can use these equations that we have to build and create some more equations, right? We know that this is equal to 0, so we can simply equal these two numbers or these two fractions equal to each other, right? So now rewriting these equations, we have r times the specific temperature, the critical point, all over Vc, or the volume at the specific critical point, minus b, the constant b squared, is equal to 2a all over v cubed, right? That is our full first equation, right? And for our second derivative here, we have 2 RT, or 2 times R times the specific temperature, the critical point, all over Vc minus B, which is the volume at the critical point, minus the constant B. This is all cubed, is now equal to 6a all over v to the 4th, right? And that is our second equation, right? So there we go. We now have our two equations, right? We have two equations. Now, what can we do with these two equations, right? Well, starting off, we can somewhat multiply them. We can simplify them so that we can find an equation for A and an equation for B, right? So what we want to do is multiply this by the reciprocal, or multiply the first derivative by the reciprocal of the second, right? So that way we have these, we know that we have these different factors and numbers, and we need to multiply them out, and we have to simplify them, right? So let's say we have the inverse of this. We now have 2RTC, VC minus B cubed all over 2RTC. So then this becomes VC minus B, right, which is the specific volume at the critical point, but to the power of 1, right, is all over 2. That's the left hand. The right hand side, we now have, instead of 6a over v cubed, we have v to the 4th all over 6a, so this becomes v all over 3, right, because Multiplying these out, we get 2a over 6a, which is only 3. And now we can start solving this simple equation that we have, right? So we can solve for b, right? We know that, I just realized that I didn't call this v the specific volume at the critical point, which is a big mistake. Just making sure to fix that. And so now we can cross multiply and simplify this out, right? So now we have 3 BC minus 3b is equal to 2 VC, right? So then, if we subtract 3VC from both sides, we have negative VC. So we have the specific volume at the critical point is equal to 3B, right? In other words, B is equal to VC over 3, right? So now we have our value for B. Now we can plug this value for B back into an equation to solve for A, right? Plug it back into this equation up here, the first derivative. Clear this out real quick so I can work it up here. Kind of working weirdly, but that makes sense. So let's plug in B, which is equal to V over 3 into this equation, right? So if we plug it in, we'll have R times the specific temperature at the critical point, right? All over, well, B is now VC over 3, so we have VC minus VC over 3, which is simply 2/3 of the specific volume at the critical point, right? That's our new denominator to the power or squared, right? This is, again, all equal to 2a over the specific volume at the critical point cubed. Right? So let's now multiply this out, right? If you multiply this out, this VC, or the specific volume squared, we'll get 4 9ths, so we'll get 9RT, or 9 times R times the specific temperature at the critical point, right? Is over 4 of specific volume, critical point squared, right? And this is equal to the same thing, 2a over VC cubed. And what we can do from here is just a simple algebra aspect that we've been using every day of our lives. Cross multiply, right? We know that we have some denominators, and if we call this multiply, we can simplify it out, right? So on the left-hand side of the equation, we would have 9 times R times the specific temperature at the critical point times the specific volume at the critical point cubed is equal to 2 times 4, 8 times A times the specific volume, the critical point, but squared, right? And we see some values that can be simplified, right? Well, we have VC squared here. Take that out, and this now becomes simply VC, the specific volume and the critical temperature. In this 8, we can divide it and put it over here, and we have a value for A as well, right? So A now becomes, is now equal to 9/8 of R, constant R, times the specific temperature at the critical point times the specific volume at the critical point, right? So now we have our A and B values, right? We have values for both of them. We know what they are. We have an equation for both of them, right? Put them right here. So now we have our two values. So the whole idea here is to solve for the compressibility factor of this, right? And as we know, the specific compressibility factor for something is the letter Z, and it is equal to the pressure times the volume all over the constant R times the specific temperature, right? And we know for an ideal gas law, that this specific Z value is equal to 0, right? But not in this, because we're not dealing with ideal gases. So the idea here is to plug in the A and B values back into the equations so that we can solve for Z, right? So that's what I'm going to go ahead and do. So going back at the equation, we know that the pressure, so numerator remains the same, R times the specific temperature at the critical point, all over VC minus B, but this is now just simply 2/3 of VC, right? And this is minus 2A, or which is minus A, where V squared, but the A is now, the A is now 9/8 all over that shenanigan, so go put that in. 9/8 of R T C E C, which is the R times the specific temperature times the specific volume over the specific volume squared. But with specific volume in the numerator, so this now just becomes VC, and the numerator becomes R times TC, right? And we can factor RTC over VC out, right? And know that they have a specific numbers, right? So if we factor that out, factor R times the specific temperature, the critical point, all over specific volume at the critical point, we would get 3/2 minus 8/9, right? Or sorry, minus 9/8, right? I don't know what I said. 8/9. And we see they have the common denominator. Multiply this by 4, we get 12/8 minus 9/8, which is just simply 3/8. So we get P is equal to the constants R times specific temperature at the critical point over the volume at the critical point, and this is multiplied times what we said, 3/8, right? If we see, we can now multiply this equation out, right? If we multiply both sides by the specific volume at the critical point and divide them by constant R and the temperature at the critical point, we would get the constant C, right? So divide it out, we get P times the specific volume at the critical point all over constant R times specific temperature at the critical point is simply equal to 3/8, right? And as we said earlier, this right here is equal to z, right? So now we know what the compressibility factor is, right? We know that it is equal to 3/8. Right? So there we have it. We used in van der Waals equation of state and solve equations for A and B, and we use those to find our compressibility factor.